Okay, I hope so. Well, thank you very much. Thanks for the invitation. It's a great pleasure to be here. And today I'd like to speak about the joint work with Lil Sela about equations in periodic groups. But let me motivate this work by some applications. And I'd like to start with the isomorphism problem. So this morning we heard about three problems asked by Dan at the beginning of the 20th century. And one of them is the dense isomorphism problem. And basically, it asks the following. So take two groups, for instance, given by their presentations. And you ask yourself if there's an algorithm that can decide whether these two groups are isomorphic. So in the class of all groups, the answer is no. You can not even decide if a group is trivial, but you can restrict yourself to some particular classes of groups. Like if you assume that your two groups G1, G2 are both abelian, then this is rather an easy problem to solve. If you assume, for instance, that G1 and G2 are hyperbolic, then the answer is yes, there is an algorithm. If I'm not mistaken, this is due to Sela and Damanian growth. And then you can ask yourself, well, is this problem solvable in your own favorite class of groups? And it turns out my favorite class of groups, at least for this talk, are periodic groups. So what are they? So fix an exponent n, just an integer, and I will say that a group gamma is n-periodic if any element gamma raised to the n is just the identity. A group in which every element has finite order, and in addition, you have a control of the order of this element. And just for the rest of the talk, I will denote by Bn the class of all n-periodic groups. Okay, so you may ask what kind of groups are like this. So there is an obvious example. If gamma is finite, you can take for n the cardinality of gamma, and well, that's an n-periodic group. But that's not very interesting. So what you can always do, this is general construction, completely abstract nonsense. If you are given a group gamma, let me write gamma to the n, the subgroup generating by the nth power of every single element in my group, so that the quotient now, gamma mod gamma n, is indeed n-periodic. So you can always do that. And somehow the question is, well, can we perform this construction in such a way that the resulting group is infinite? And so there is a long history of results in these directions. So the first one is due to Novikov and Adian. And then there is a version by Olshansky, and some proof by Delzan and Gromov. The statement would be the following. Assume that gamma is a non-elementary quotient-free hyperbolic group then you can find some critical exponent big N, so that for every odd integers larger than this big N, the quotient gamma mod gamma N is infinite. So the original result by Novikov and Adian was for gamma being the free group, and then there has been an alternative proof by Olshansky, and then Olshansky and both Stelzner and Gromov, they prove this kind of statement. So just to mention that there are interesting infinite groups in this class. Actually, they have a lot of groups. The class actually is so wide that one can prove that if you restrict yourself to the class of all n-periodic group, then the isomorphism problem is still not solvable. Sorry? Yeah, the triviality problem too. That's why it's not. And this is some work of myself with Dominic Gruber, and it's based on a construction. Yeah, for large M, and I'm cheating a bit. This is for n which are not prime. So that's based on the construction by Olga Karlampovich. So Olga produced an example of a group in Bn for which the world problem is not solvable. And from there are sort of classic construction, let's say, to prove that the isomorphism problem is not solvable in this class. So just some evidence that this is a weird class of groups, which is somehow as complicated as the class of all groups. And so because the isomorphism problem is solvable for hyperbolic group, and in view of this theorem, you may wonder, well, what's happening if we restrict ourselves to periodic quotient of hyperbolic groups? If we just look at those, can we solve the isomorphism problem? So actually, I have a more precise question. That I can formulate in this way. So take two quotient-free non-elementary hyperbolic group. So obviously, if gamma 1 is isomorphic to gamma 2, then gamma 1, well, the nth periodic quotient of gamma 1 is isomorphic to the nth periodic quotient of gamma 2. Question, is the converse true? Somehow, does this periodic quotient remember the isomorphic class of my original groups?
These are isomorphic for all n, does it imply that they're isomorphic?
I'll come to that in a minute. So that's a very good question. So of course, well, I don't know if of course or not, but in this set of, this level of generality, there is no way that the answer is yes. And there are some obstructions. I'd like to go through with you these kind of easy obstructions. And the main idea is that behind those obstructions, everything goes well. So my first obstruction is related to your question about exponents. So let me give you an example. I'll take gamma 1 to be the free group generating by A and B, and gamma 2 to be a group with the following presentation, have two generators A and B, and I ask that say some very complicated word in A to the n and B to the n equals 1. So this group can be made torsion-free hyperbolic by some small constellation argument. And well, one observed that, well, gamma 1 mod gamma, the nth periodic quotient of gamma 1 is isomorphic to the nth periodic quotient of gamma 2, because if you kill the nth power of every element, this relation is completely trivial. But there is no way that gamma 1 and gamma 2 are isomorphic. So the reason is that this gamma 2 has something very specific with this integer n. But one can observe that if I choose another exponent very large compared to n, then this is no more true that gamma 1 mod the nth power of gamma 1 is isomorphic to gamma 2 mod the nth power of gamma 2. So I will have sort of an asymptotic point of view. I want to ask myself if those two periodic quotients are isomorphic for some large n, and the large n may depend on my groups, as this example shows, does it mean that gamma 1 and gamma 2 are isomorphic? So that's it. However, there is another obstruction which is a bit more subtle. Which is the following. So now I take again gamma 1 to be the free group generated by A and B, and gamma 2 will be generated by A, B, and C, and as I add as a relation that C squared equals some weird word, say, in A and B. This one can be made torsion-free hyperbolic using a Bézuna-Fein combination theorem, for instance. Now, look at the following. Imagine that n is an odd integer that I write as 2k plus 1. If I consider the nth periodic quotient of gamma 2, inside this quotient, the relation c squared equals w of ab, this is exactly the same as saying that c equals w of ab to the k. I'm just saying differently, that in z mod n, if n is odd, every element has a square root. So you see, if I go to the nth periodic quotient of this gamma 2, the extra relation I have here is not needed. I can drop it. And C will be just certain word in A and B. So it means that the nth periodic quotient of gamma 2 is just the same as the nth periodic quotient of gamma 1. And this time, if I increase my exponent, I will not fix this problem. So here there is really something going on that tells you that in general, this answer to this problem is no. So in order to formalize a bit this idea, I will say that a group G admits a root splitting if I can write G as an amalgamated product of this form, where B is abelian and C as finite index in B, which is typically the case here, where C would be the group generated by C squared, and B would be the group generated by C. And well, let's just to finish with vocabulary. I would say that such a splitting is non-essential if C is a free factor of A and B is abstractly isomorphic to C. So why do I say that those ones are not that important? Because, for instance, you can always write the free group with two generators as a group generated by X and Y squared amalgamated with Y over Y squared. So this is sort of a silly way to write the free group, and you don't want to take into account this as root splitting. And so more generally, following these examples, one can show that if you have a group with a root splitting, if you take an exponent n which is co-prime with this index, G mod G to the n is isomorphic to A mod A to the n. So this is kind of pathological splitting for a group regarding these questions. But the good news now is that that's the only joke that may happen. Oops. Not very far. Okay, so now I'll be ready to state theorem. So the way I write it now, I think it's, well, it is not in our paper, but I realized last night that it is, we can prove something slightly better. So I'm hoping I did not make a mistake. But the idea is the following. So you take gamma 1 and gamma 2, which are two, again, non-elementary, torsion-free haplogroup groups. And I will ask that they are both without root splitting. Then one can find some critical exponent n such that for every, such that the following are equivalent. First, gamma 1 is isomorphic to gamma 2. Second, gamma 1 to the n, the nth periodic quotient of gamma 1 is isomorphic to the nth periodic quotient of gamma 2 for every integer n. And third is that the same holds, but just for some odd exponent larger than n. So it suffices to know that for some large odd n, these two nth periodic quotients are isomorphic, and you will directly recover that the two original groups are isomorphic. So that's sort of a very surprising thing. Well, it was very surprising to us that these actually capture the all isomorphic class, isomorphism class of my original groups. You don't need to have all exponents.
Well, sorry? If you remove the root splitting without root splitting assumption, then
Well, you still have this kind of example.
But if you remove those, like if you look for n even, for instance.
Okay, well, maybe first one comment. I will always assume n is odd.
Okay.
There are some reasons. First, proving that Burnside group are no, that's a very good question. Proving that periodic groups are infinite for even exponents is not a piece of cake. And in the strategy we are using, this will completely fail for the moment we don't know how to handle even exponents. Other questions? Sorry? No, the really relevant problem is the even exponent. As soon, for instance, if n is odd, those periodic quotient, if you look at the finite subgroup, there will always be subgroup of z mod n. That's the only possible finite subgroup you can find. If n is even, you may have arbitrarily large direct product of dihedral groups embedding inside this thing. They're completely different behaviors. But there really is a problem with even exponents that will create dihedral groups somewhere. At the
Hyperbolic group, can you decide whether it has a root splitter?
Sorry?
If you have a hyperbolic group, like its algorithm can be decidable whether it has a root splitting. Or not.
I'm not completely sure, but I guess if you look at
Like, for example, you have two hyperbolic groups, can you decide whether you can apply the theorem, for example?
I did not think about the question, but I would not be surprised if it is decidable.
B is a billion, right? So you can find a billion splitting, so it's maybe
Yes.
decidable.
Other questions? Yes?
Big N depends on both gamma 1 and gamma 2.
Yeah, so, I just read that example, but that first example I gave you show you that the big N has to depend on gamma 1 and gamma 2. There is nothing else.
Another question. So can you see all elements of gamma in some periodic quotient? Like, do these periodic quotients separate points?
Yeah, so somehow every finite set of gamma 1 mapped injectively in the periodic quotient if you choose n large enough depending on your finite set. So you're all one-to-one on larger and larger balls if you let the exponent goes to infinity. I think somehow you try to invert some two limits somehow. You won't say that, or if you assume that those two groups are isomorphic for every n, it means your balls in gamma 1, gamma 2 looks more and more alike. And you would say, well, the groups are actually isomorphic. Sadly, it's not as easy an easy argument, but that's, I guess, one feature to keep in mind. Okay, where I am. Yeah, so maybe I'd like to add one or two more applications to refine a bit this picture. So in particular, if you assume that gamma 1 and gamma 2 are fully indecomposable, then you can be even more precise about this result. So that's another statement that we have. So now I will assume that gamma is, again, non-elementary, torsion-free, hyperbolic, now fully indecomposable, and without root splitting. And I claim the following. So there exists, again, some critical exponent such that for every odd exponent larger than this big N, first, well, anytime you take an automorphism of gamma, it sends the nth power to an nth power. So just saying that the group generating by all the nth power is characteristic, so that induces an automorphism of gamma mod gamma n. And it turned out that in this context, this map is onto. So somehow it means that if you have such an isomorphism, the isomorphism you have between the periodic quotient lift directly to an isomorphism between the original group. It's not any abstract result, really just any isomorphism lift. And this is even more rigid in the sense that gamma mod gamma n is co-option, meaning that every injective morphism from gamma n to itself is actually onto. So the possible self-morphism of gamma n are actually very rather limited somehow. And this is maybe to relate to this similar statement for hyperbolic groups. So torsion-free, freely indecomposable hyperbolic groups also have this property of being co-option. Somehow we have the same thing at the level of their periodic quotients. Okay, so what's now are the idea behind the scene? But everything boils down to solving equations in Burnside groups, in periodic groups, sorry. So more precisely, if you are given a group G, given by a certain presentation, what we want to study is all possible homomorphism from G to some periodic group gamma mod gamma n. So an equivalent way to think about it is you consider that x1, xr are unknowns, your relations are equations, and you ask yourself, can you solve this set of equations inside gamma mod gamma n? And any solution actually is given by such a homomorphism. That's completely one-to-one dictionary. So we try to understand what are this set of homomorphisms, or equivalently, what are the solutions of a given set of equations. And if you think about this sort of lifting idea, the question we have is a lifting question as well. So let's start with a simple remark that there is always a map from the homomorphism from G to gamma to the homomorphism from G to gamma mod gamma n, which takes a map phi and sending to phi composed with phi, where phi is just a canonical projection. This is just a very fancy way, or maybe pedantic way, to say that if you have a solution to an equation gamma, you project it, and that gives you a solution in the periodic quotient. It's just what I'm saying. And somehow the question is, when is this map onto? Say differently, under which condition on my set of equations, every solution in gamma mod gamma n comes actually from a solution in the original group gamma. Well, we will face similar difficulties than for the isomorphism problem. So if G has some roots, then there may be some jokes, and it might be hard to lift my solutions.
G is the free Burnside group of rank R.
No, G is just, you can think of G as a way to encode a set of equations. So now G is just any finitely generated group given by a presentation. And the relations, you can interpret them as equations with unknowns x1 to xr. And every such morphism is just a solution to this set of equations. Is it clear? Yes?
Sorry, so seeing this, does this mean that actually in your theorem, what you're saying is that these isomorphisms between periodic quotients actually lift?
So only in the one-ended case.
Sorry?
Only in the one-ended case. In the free decomposable case.
Okay.
Like you have automorphism of, if you take gamma to be the free group, this we would call the free Burnside group, and you have automorphism of the free Burnside group that do not lift to automorphism of the free group. Nevertheless, it's easy to see whether they are isomorphic. You just look at the abilization, for instance, and you see they have the same number of elements. So the isomorphism class can be encoded by something else than just an explicit automorphism. So let me give you a statement where this answer will be positive. So I will assume that G is a finitely generated group, and my assumption is quite strong. I assume that none of the quotients of G has an essential root splitting. And now I consider gamma to be a non-elementary torsion-free hyperbolic group. And then I claim that there exists some exponent n, so that for every odd integer n larger than this big exponent n, for every morphism from G to gamma mod gamma n, whose image is not abelian, there exists a morphism from G to gamma, phi tilde, lifting G. So, roughly speaking, I'm just saying that if no quotient of G has a root splitting, then morphism from G to gamma mod gamma n will lift. You just have to be careful because imagine your G is something like Z mod NZ. You will not be able to lift these to morphism to a torsion-free group. So this is why I ask that the image of phi is not abelian. That's the only other joke that may happen. Okay, I don't care.
This is something, what if G is just gamma mod gamma n?
If G is just gamma mod gamma n, so yeah, maybe let me emphasize this way, that this critical exponent here does depend on G. So this is an asymptotic approach. Somehow we could have done two things. Fix an exponent n and look at all possible equations and try to solve each of these equations in gamma mod gamma n for fixed n. Now we do the other way around. We fix our set of equations, or we fix the group G, and we ask ourselves, for sufficiently large exponent n, can we solve the system of equations? So if G is gamma mod gamma n, maybe if I move to a much larger exponent, I have two different exponents, and probably there will be no such maps. So there is no contradiction. It can be an infinitely presented group. Yeah. Yes?
Hyperbolic groups are needed.
Well, let me move to the last part of my talks. I want to give you a few ideas about how such a statement is proved. Well, first, everything I wrote here are variations, well, consequence of variation of this kind of statement. And how we solve this? This is where we step on the shoulders of giants, because there are many techniques which have been developed to understand equations in groups with some kind of negative curvature. And this is what we want to use. And somehow, this is where all the geometry and dynamics is hidden. I'm sorry it comes that late, but that's the trouble with this topic is if you want to set up the whole background, it takes a little time. So, idea behind the proof. Yes? Of G, for instance, you take a group with property T. That's very brutal, but a group with property T cannot act on a tree without a global fixed point. And so if a quotient has a splitting, well, the splitting will act on the Basel tree. And therefore, the group G would act on this Basel tree with a non-global, without a global fixed point. So that's an example. You have more refined examples, but yeah, FA, for instance, is enough, and you can, you know, if you know about the other things, you can cook up more precise examples. Other questions? Okay, so the idea behind the proof is by contradiction. Assume that such a statement is not correct. So if you do your exercise, it means that for every big n, there is a small n, there is an morphism. So you produce a family of counterexamples. You derive a family of morphism phi k from G to some periodic quotient of gamma, where nk goes to infinity and phi k does not lift. At this point, well, experts in the audience may notice that if instead of having a periodic quotient here as a target, had a fixed hyperbolic group, the same for all k. If such a thing happened, then there is a whole machinery which is available that for each morphism, imagine for a second, I replace here this fixed, this varying group by a fixed hyperbolic group. And each morphism defines an action of G on a hyperbolic space, for instance, the Kelly graph of H. And very likely, all these actions will degenerate to an action of G on a real tree. And from there, this is where I said you step on the shoulders of giants. When you have such an action, you have the RIPS machinery, which gives you a decomposition of your action on R tree and giving you some splitting of a certain quotient of G called a limit group. And then from there, you have another big tool, which is called the shortening argument, which allow you to say, well, if you had started with the simplest possible counterexample, actually there is an even simpler one. And there you will reach a contradiction. That's all the general framework. The trouble is, the group here varies and is absolutely not hyperbolic. If you try to have this group acting on a hyperbolic space, well, either it has a bounded orbit, it's elliptic, or it acts like a parabolic subgroup. So there is no way we can extract information from an action of gamma mod gamma n to the k on a hyperbolic space. Now the trick is the following, is that those quotient, periodic quotient of hyperbolic groups can be very well approximated by hyperbolic groups. So what do I mean by this? When you have this quotient gamma mod gamma n, you can find a sequence of groups gamma naught, well, which is actually gamma, gamma 1, gamma 2, etc. A sequence of actually hyperbolic groups such that the direct limit of this gamma I is my gamma mod gamma n. So imagine for a second that my group G is finitely presented. That will imply that I can lift my morphism phi k from G, which was from here to here. I can lift it from here to some of my approximation group, because all the finitely many relations have to be satisfied at some point in this approximation. So I reduce my problem to solving equations captured by G inside a class of hyperbolic groups. So I'm back to hyperbolic groups, but varying hyperbolic groups. And then there is some work related to this approximation to say that we have some uniform control on the geometry of those hyperbolic groups, so that all the machinery I sketched in the context of hyperbolic group still work here. Somehow the sort of miracle is when, as k goes to infinity, the exponent also goes to infinity. So the sort of limit group that appears are torsion-free. All the torsion has disappeared. But in this Ripps decomposition, we have a certain new type of component that appears, and that is annoying to run the shortening argument, and is really related to this root splitting that we have seen so far. And I'm already out of time, so I will stop here. Thank you.